Hello there, Mr. Chan here for Algebra 2, about to start 6-4 called Logarithmic Functions. Please grab your note takers and turn to page 153, and let's get started. We have an opening here looking at three different graphs. They should look kind of familiar. Compare the graphs, there are three of them. These are definitely all parabolas. Which two graphs represent the inverse of each other? Now, the word inverse literally means the actual technique is to swap x and y. If you had an equation, and when you graph it, it is a mirror image, literally about the line y equals x. Y equals x is a diagonal line. Let's draw that into all these right here. Y equals x. A mirror image. Which of these two are a mirror image of each other about that diagonal line? And obviously we see these two are inverses of one another. Okay? In fact, the first one is literally x squared. The second one is the square root of x for the top half and negative square root of x for the bottom half. The third parabola is actually a parabola that has been reflected vertically. That one's negative x squared. And you can kind of see that. This might be a great time to go grab your graphing calculators or load up Desmos. And as you can see here, I have a screenshot of x squared. And then if I turn on these other two right here, boom, there it is. Mirror image of the two functions along the line of y equals x, the diagonal line that goes this way, okay? And of course, the third one is y equals negative x squared. That one is not a mirror image. It is a mirror image vertically, okay? That has reflection that way, but not along the diagonal as an inverse. All right, great. Let's go back to our notes here and continue with this opener here. Second question. What is the relationship between the domain and range of the two inverse relations? Now, when I say swap x and y, I'm literally changing the domain and range. So let's note that. The domain and range are swapped. When you compare the two different functions. Next question. How are the points on graphs of functions that are inverses of each other related? So literally, along the diagonal y equals x, let's just randomly pick a point, let's say 1, 5, which would be a random point for, say, one of the functions, x, y. The swapping of x and y will give you 5, 1. Right there. They're literally a swap. Mirror image of each other. Okay? That's what it means. It's a mirror image. All right, let's jump to the next page. Let me know if you have any questions throughout this lecture. A lot of things going on here. We just introduced the idea of logarithms last section, 6-3. I want to remind you, when you're converting between exponential to logarithmic, this is what we have, okay? B of y equal x is equal to log base b of x equals y. That is a relationship. Remember the idea of a boomerang? The boomerang is the base is equal to a power, the y value right there, and the power is over here on the other side. So like a boomerang, it's like you're throwing it over the fence this way. Draw an arrow instead, okay? And most boomerangs, unless you throw it really bad, come back. And what it comes back to is something called the argument or the answer. Okay? And that's how you utilize the log function on your calculators. It can figure out the answers for you. We used to have log tables or these pages of things that are in the back of our book that we looked up for answers. To find the inverse of this relation, the key is to swap x and y. So here, literally taking b to the y equals x, and when you swap x and y, you get b to the x equals y, okay? So keeping that in mind, and keep in mind what we're about to do for example 1, we need to utilize inverses to graph certain log functions with different bases other than 10 or e. Now, base 10 and base e was something we briefly talked about in the previous section. It's called the common base. And the other one, base e, is the natural base. These are built into our calculators or in graphing calculators, okay? But here's the weird thing. What if your base is not 10 or e? How do we graph that? That's the question. We have to utilize inverses to do that. It's kind of like a roundabout way of doing problems when it comes to technology. Let me explain more. I'm going to actually add example 1 from the book first before we do the example 1 over here in the note taker. Here we go. Please bear with me. We'll call this 1. Graph y equals log base 2 of x. Now the majority of calculators are base 10 and base e. We do not have a base 2. So here, to graph it, we have to go in a roundabout way of doing this. We need to find the inverse then graph it, and graph its inverse, which goes back to the original problem, log base 2. We're kind of like going one way and then back the other way to just show the actual graph. Okay, it'll be more explanatory when I get to there. Here we go, let's try one, okay? All right, here we go. So the first rule of finding the inverse is swap x and y. Let's do that. X equals log base 2 of y. Notice how I swapped the x and the y right there. Okay? Second step, solve for y. Now, unfortunately, y is buried in the log function. I can't just divide it out. That's illegal. However, it's in log form right now. I'm going to convert that to exponential form. Whoops. So this is a strategy. Convert from log form to exponential form. All right, let's take a look at our log form here. Look for the base. Very nice. The base is 2. Okay, to the power of, it's on the other side of the fence, x. And boomerangs come back. That equals to y. Hey, we know how to graph 2 to the x. We've done that before. That's an exponential function. Let's draw that. Oh, and they want us to find the domain and range, list any x-intercepts or asymptotes, and describe the NV here. A lot of little things going on here. So let's do that here. All right, thanks for hanging in there. This stuff gets a little bit weird, doesn't it? So we're trying to graph y equals log base 2 of x, but most calculators and graphing calculators cannot graph these because the base is not 10 or e. We don't have a button for base 2. So we have to graph its inverse right now, 2 to the x equals y first, okay? So just pick a couple of points. That's very easy, right? Very easy. 0, 1, 2 to the 0 is 1, 2 to the first is 2. Plot those 2 points. Easy peasy, 0, 1, 1, 2. Look familiar? This is exponential growth, right? From left to right. So I'll just draw that in blue. Yay, there it is, ladies and gentlemen. That's 2 to the x power. And guess what? Now I'm going to graph the inverse of this inverse, and that'll give me back to the original problem, y equals log base 2 of x. So those 2 points, 0, 1, and 1, 2, I'm going to go ahead and swap them. Okay, 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. And it's a mirror image along the diagonal y equals x. And when I graph the inverse, I'll get this. Bam. There it is, ladies and gentlemen. This is the original problem, y equals log base 2 of x. That's what I wanted originally. Okay, let's see. They asked for any type of intercepts. Oh, it does cross the x-axis right there. That's the x-intercept at 1. Great. They asked for the domain and range because there are no other intercepts. Great. Let's talk about that. The domain, of course, is, this section right here looks like it's all positive x values. Doesn't hit the 0, right? X cannot equal to 0. That doesn't exist. That's a vertical asymptote, actually. So let's throw that in. There's a vertical asymptote right here that helps guide the inverse of 2 to the x. So that right there is an asymptote. In fact, it's a vertical asymptote at x equals 0. The domain is greater than 0 because it's going to the right of the vertical asymptote. And the range is a little easier. The range is up and down forever, right? Ooh, all real numbers. Yay. Not too bad. What do you guys think? Vertical asymptote? Oh, they also asked for end behavior. Great. A little more work there. Now, end behavior is about how a graph is graphed from left to right. So let's talk about end behavior really fast. End behavior is from the middle. Did I say from left to right? I meant from the middle. I misspoke there. I was thinking of increasing or decreasing. They're not asking for that. We're asking for from the middle. What's happening to the ends from the middle? Sorry about that. So from the middle, my function, let's see, is going which way? It's going down to negative infinity, right? That makes sense. So let me write that down. As x approaches left, meaning negative infinity, my function value, y, is approaching negative infinity. If I'm going left, it's going down. How about to the right? As x goes to the right, positive infinity, it doesn't look like it's going up, but it is definitely still going up. Looks like it's slowing down, but it's not. It's still going up forever. So that's going to be positive infinity. Okay? Great. How are we doing out there? So if we switch to Desmos, I'm going to show you that relationship there. 2 to the x, bam. And log base 2 of x. Now, Desmos does allow you to graph base 2, but most graphing calculators don't have that ability. So we're using this technique of graphing the inverse in red and then flipping it graphically, visually on our paper for the actual problem in the first place. That's the strategy. Let's move on to the next one. Ooh, this is an interesting one. Same directions like the one we just did a second ago. Let's graph y equals the natural log of x. Now, I want you to think of this as log base e of x, okay? Think of it that way. ln is natural log. It's so special, log base e, that they give it its own name. But it's basically log base e of x, okay? So the technique here is to swap x and y. Oh, by the way, I set that equal to y. So let's swap x and y. We're going to graph its inverse first. Okay? So we have now, not a lot of room here, I apologize. Log base e of y equals x. And then solve for y again. Now, it's in log form. I'm going to swap it. I'm sorry, not swap it. Change it to exponential form. The base is e. Let's change it to exponential form right now. That's the key. The base is e. And we're flinging the boomerang to the other side. That's x. Nice. And it comes back. Woo, to y. Very nice. There it is. Graph that, and then graph the inverse of that inverse, so you get back to the original problem. Now remember what E is. E is a irrational constant that's they call the natural base that's linked to how things grow in the universe. E is 2.718 approximately. Now, this shouldn't be too much of a stretch, and I'll say this. 2.718 is basically the same as kind of like this. 2, right? In terms of a plane taking off, you're going to get the same thing. So graph-wise, let's throw that in here. Let's graph e to the x right now. And if I use a t-chart, 0, 1, e to the 0 is 1, e to the first is 2.718, right? That's easy to do. Let's plot those. 0, 1, 1, 2.718. Hey, it's just like the last problem, basically. Yeah, basically the last problem. The base obviously is a little bit bigger than 2, but there it is. Let's go ahead and graph the inverse of that, which will eventually be the natural log of x. Throw in the diagonal, and then swap the coordinate points. 0, 1 becomes 1, 0. 1, 2.718 is now 2.718, 1. Okay, great. Let's graph that. And here it is. Whoa. Essentially the same as the last problem, pretty much. We do have a vertical asymptote we don't want to forget about. Vertical asymptote is x equals 0. We do have an x-intercept again. It's at +1. They do ask us for domain and range again. The domain is just like the one we did down there. X is greater than 0. The range is all real numbers, just like the last one. Okay, and behavior is exactly the same. It's from the middle, of course. As x goes left, right? Remember going left? What's happening to my y value? Okay. The y value is going down. Left, down. As x goes to the right, just like the last one, right? Oh, I never wrote those down. Whoops. My bad. This is right, and this is going up. My y value is going up. Okay. Not that exciting, just like the last one we just did. But it's good that we're using natural logs. Ooh, letter B. Look at that base, 1/2. We don't have that built into the calculator. Oh, by the way, let me show you what that looks on decimals really quick. Shouldn't take too long. Turn that off. I'll have e to the x and natural log of x. Yay, there it is. All right, let's come back. Okay, so swap x and y. And solve for y. X equals log base 1/2. That's kind of interesting to the y power. Isolate y, I need to convert it to exponential form in order to read that properly. Let's do that and zoom in a little bit so we'll see a little better. There we go, much better. The base is 1/2. The power's on the other side, x, and that equals 2y. Hey, there it is. My base is 1/2. Oh my gosh. This particular problem is a little bit different. The base is 1/2. It's no longer a growth, it's a decay. This is a decay exponential function. Quick t-chart here will show you that. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. So this is interesting. Let's graph those. When you graph that, you'll get this function right here. All right, that is 1/2 to the x power. Yep. Throw in the diagonal, because I'm now manually going to swap those two red dots now. So instead of 0, 1, I'm going to graph 1, 0. And instead of 1, 1/2, I'm going to graph 1/2, 1. Interesting. So the graph is going to look very close to each other. It's hard to do here. Forgive me. Okay, here we go. There it is. What do you guys think? Okay. That, ladies and gentlemen, is log base 1/2 of x. Interesting. The y-intercept is still, I'm sorry, the x-intercept is still 1. Actually, a lot of things are still the same. Interesting. But the end behavior is a little different. Okay, I will say that though. My vertical asymptote is still x equals 0. Fine. Domain and range are kind of the same. Domain, oh, my bad. I confused range with that. Domain is to the right of the vertical asymptote, so x is greater than 0. My range is all real numbers. The end behavior is a little different this time. Okay, you got to be a little careful here. So end behavior, let's go and list that. As x approaches left, y approaches what? As x approaches right, y approaches what is the question? All right. So from the middle, if I go left, it's going upwards. So that's positive infinity. I go left. Interesting. And if I'm going to the right, it looks like it's bottoming out, but it's actually still going on forever this way. It's going downward, okay? It's hard to explain. You just have to visualize that extended forever. It does go down to negative infinity. All right. Any questions? That takes care of example 1A and 1B and the one I threw in all together. How are we doing? It's a lot so far. Woo. All right. Let's move to example 2. Graph the transformations of logarithmic functions. Describe how each graph compares to the graph of L and X. All right, fine. The natural log of X, we graphed right there from earlier, okay? The points are right there 1, 0, and E1. Okay, those are the points. Just remember what that looks like, okay? That's your parent graph we're going to be using for example 2, right there. Great. So jumping down to example 2, I'm going to draw in some axes for these two problems. And with any type of transformations, we have our A's, H's, and K's, ladies and gentlemen. It's that easy. If you know what the graph looks like, you can manipulate. Y equals A times the natural log of X minus H plus K. Just a quick reminder, A, of course, is a vertical stretch, shrink, and reflection. H, of course, is horizontal movement, left to right. K, of course, is up and down. Vertical, shifting left, up and down, up or down, okay? All right, let's take a look at number 2a, ln x plus 4. I don't see parentheses. That 4 is not h. That 4 is k, ladies and gentlemen. Which means I'm going to go up 4 from my parent graph. Now earlier, natural log from example 1a looks like this. This is the natural log of x. All we have to do is to shift this up 4 units and you're done. 1, 2, 3, 4, and I'm kind of concentrating on that x-intercept right there to help me do that. Okay, so go up 4 units, 1, 2, 3, 4, and you're done. I want to mimic the black dashed line onto there, showing me shifting up 4 units, and you're done. That's ln x plus 4, up 4. Easy peasy. All right, I'm going to do the same with number 2b now. Go ahead and graph in my thing. This was a little trickier with the 5. That 5 is definitely A, isn't it? That's a vertical, and 5 is 500% stretch by 500% or just 5. That's fine. So after you draw your parent graph here, ln x, imagine stretching that vertically by a factor of 5. That's kind of hard to see. I might have to utilize a bunch of space here, to be honest with you. 5 times, that's crazy. This point, let's just pick a random point here. I'm just going to draw it. Let's just draw it. It's easier to see it, okay? I'm going to draw something that's 5 times off the, yeah, this will be work. There we go. This is an approximation. It's been stretched 5 times. All right, not too bad. And note, by the way, both of them, their vertical asymptotes didn't really go anywhere. I wanted to note that. We're not shifting left to right, just up and down and stretching it up and down, so it doesn't really change that. All right. Speaking of H's or K's, let's take a look at our habits of mind here. In the first equation, y equals ln x plus 4, that plus 4 is on the outside of the function, so that is definitely k. So that means it's up 4. The second function, the 4 is on the inside. You got to think backwards. This is h, negative 4, which means it's going left 4 units. So that's how those relate to the original function, ln x. Okay? Up 4 is different from the other one, left 4. Very good. Let's go to the next page. Yay. Example 3. Oh, okay. No more graphing. We're moving away from graphing. We're actually going to find algebraically the inverse of each function. Doesn't matter. They just throw a bunch of stuff at you. Force field. Let's go ahead and change that f of x to y. Just a quick reminder to find the inverse. Swap x and y. And then, of course, isolate y. Algebraically, okay? So here we go. Let's swap x and y right now. In that first equation. Nice. Let me zoom in a little bit more so you can see it better. There we go. We have x equals 3 to the y plus 2. Oh no, I don't know how to bring that y out of that power position. However, we have this ability to switch between the two forms. Right now, it's an exponential form. Our suggestion is to convert it to log form. So let's do that. Ready? Write down log first, and then equals. The base is the number by itself, right? The little guy right there. That's the base. Put it right there. To power of x plus 2. The power is on the other side of the fence. Oh, did I say x plus 2? I meant y plus 2. Boom, there it is. And that equals to x. So the boomerang comes back to that. Hey, look at that. Log base 3 of x equals to y plus 2. Almost done. I had to isolate y. Let's subtract 2 to both sides. Now be very, very careful here. Y equals, that minus 2 is not part of the x, so there's no parentheses. There it is right there, okay? And there's your equation. Now officially, we're going to use inverse notation to represent the inverse. So instead of y equals, we'll use f of -1 equals 2. And there's my equation, yay. Not too bad. All right, let's try letter B. Again, this is just all algebra. Y equals log base 7 of x minus 2. That minus 2 is not part of the function log. Swap x and y right now. We'll get x equals log base 7 of y minus 2. Now, here's something I didn't mention earlier. Before I can change it to the other form, you must isolate x. I'm sorry, you must isolate the log function, okay? So be careful. Right now I have a minus 2 kind of like attached to the word log. I want to isolate this first before we convert it to the other form. Let's go and add 2 to both sides. All right, so x plus 2 equals log base 7 of y. Now I can convert it to exponential. I'm sorry, to log, I want to convert from log to exponential now. Because remember, the letter y is buried inside my log function. I can't divide it out. Here we go. Let's do this. Base is 7. Nice. So let's write that down. 7. The power's on the other side. The other side's the whole thing. X plus 2. Crazy? Yeah. And boomerangs come back to the argument. In this case, y. Ladies and gentlemen, there's your answer. 7 to the x plus 2. You're done. Any questions? All right. The next problem is a word problem. Don't be afraid. It's the same as example 3 and 3b. Here's the actual word problem from the book. It's not written here in the note taker. R equals 12 times the log of a plus 1, close parentheses, plus 25. Don't worry about where that came from, okay? Don't worry about it. It's just something to do with advertising budget, sorry. Here, what are we trying to do, you think? Yeah, we're trying to solve for A. Okay, that's all we're doing. So before we do that, what you want to do is we want to isolate the log only. We got to move the 25 and the 12 to the other side. Let's do the 25 first because that's order of operations backwards. Nice. So we have r minus 25 equals to 12 log a plus 1 in parentheses. Next, I want to get rid of that 12. Let's divide by 12 to both sides. Great. Yes, we're getting an ugly mess here, but the 12s go away. Log of a plus 1 equals to r minus 25. Don't worry about what that is, over 12. Now, I need to solve for a. Now, unfortunately, it's in log form. We want to convert from log form to exponential form. All right, here we go. Let's look for the base. Whoa, whoa, whoa. Where is that little number, Mr. Chan? Well, it's invisible. The base is 10. If it's not there, then it's the common base, base 10. 10 to the power on the other side. Boomerang. Wait a second, Mr. Chan. Wait a second, Mr. Chan. The other side is this whole ugly mess. And guess what? You're right. The whole ugly mess is the power. R minus 25 over 12. Boomerangs come back. Right there. That equals to a plus 1. Yay. There it is. We need to isolate a. One last step, subtract 1 to both sides. And that's your final answer. A equals to 10 to the r minus 25 over 12 minus 1. Now, for those of you who have gone through a good amount of science classes, you might remember seeing some formulas with the word log in it, or exponents. And the way I manipulated this particular formula is how the science folks rearrange, isolate, and solve for another variable. You have to utilize the idea of converting between log and exponential form, okay? Okay. How would you explain in your words how to find the inverse of a log function? Well, we talked about this already a few times. Let's do it one more time. Isolate the log function before swapping x and y. I had to show you that midway up there when it came to problem numbers 3a and 3b, okay, and also with example 4. And then after you do that, you want to, of course, isolate y from there. All right. Let's move on to number 5 here. Notice that number 5 has some problems. It's about rate of change. That's fine. But this problem has so many problems with it last year that we realize it's not worth our time. We're going to skip number 5. And we're going to jump to the last page if you guys don't mind. Here we go. Woohoo! All right. Logarithms. Graph the function y equals log base 4 of x and identify the domain range. List any intercepts or asymptotes to describe the end behavior. Now, we know we can't just punch this in the calculator because it's base 4. We're going to graph the inverse of this function and then graph the inverse of the inverse to graph the original problem in the first place, right? The roundabout way that we did in the beginning of example 1. So let's go ahead and do that. Let's go ahead and swap x and y right now. That'll give me x equals 2 log base 4 of y. It's in log form. Let's convert it to exponential form and graph it from there. The base, of course, is 4. Boomerangs to the other side, and it comes back to y, okay? That's how we rewrite it in exponential form. So base is 4 to the power of x. That equals to, oh, there it is. We've done this before. We did 2 to the x and e to the x. So it's no wonder when we graph this, it's pretty easy. 4 to the 0 is 1. 4 to the first is 4. Let's plot those. 1, 2, 3, 4. 1, 2, 3, 4. 0, 1. 1, 4. This is my 4 to the x function. Let's graph the mirror image of it through the y equals x line. Okay. 0, 1 becomes 1, 0. 1, 4 becomes 4, 1. I'm swapping the domain and range now. Remember that, okay? And the equation I have and the graph I get is this guy right here. Whoa. We did that 3 times already, so it shouldn't be too much of a surprise. They do want to look for any intercepts or asymptotes. Asymptote is still there at x equals 0. That's a vertical asymptote. Nice. We have an x-intercept right there. Nice. And domain and range is just like what we do with example 1 and 2, I believe. Domain, it looks like to the right of the vertical asymptote, x is greater than 0, and the range is up and down forever, all real numbers. In behavior, we've done that a few times already. As x approaches left, and the other one as x approaches right of infinity, what happens to the y value, right? Okay. That infinity looks kind of funny. Better change that. Whoops. So when I'm going left from the middle, I'm dropping downward to negative infinity. And when I'm going to the right of the graph, I'm going, it doesn't look like it, looks like I'm bottoming, I'm like leveling off. I'm not, I'm actually going to positive infinity. Okay? Yay, not too bad. All right, let's move on to number 5. Write the equation for the function g of x, which can be described as a vertical shift 1.5 up from the function f of x equals ln x minus 1. So this is kind of just interpreting the actual graph itself. Up 1.5 is k. It's kind of weird, right? And don't forget our formula, a times ln of x minus h plus k. I'll take the function, right? Take the function, call it g of x. Oh, you might as well use some more. What we want to do, we want to take the function f of x and add 1.5 units, right? F of x, of course, is ln x minus 1 plus 1.5. This equals ln x. Negative 1 and plus 1.5 is plus 1/2. And that's it. It's kind of boring, actually. Not that exciting. But the point is, they want you to be able to interpret the function notation and utilizing that, okay? Yay, there it is, ln x plus 1/2. Number 6, last one. The function y equals 5 times the natural log of parentheses x plus 1 gives y the number of downloads in hundreds. So I think that's what we're talking about music here. X minutes after the release of a song. Find the equation of the inverse. Okay, fine. So we'll take our equation. Swap x and y. Let's do that. Nice. And solve for y. The y is buried in the function. I need to convert it to the other form. Now, be careful here. Before I can isolate before I do this, I have to isolate the log right there. That 5's in the way. Divide by 5 to both sides. That's what I wanted to blurt out there. All right. Now I want to convert to exponential form from log form. Right? The base. Now, ln has a base e, okay? Boomerang it, to the other side, and it comes back to the argument, okay? So this is e to the x over 5 equals 2, y plus 1, almost done. Subtract 1 to both sides. And there's my inverse, yay. E to the x over 5 minus 1. Ladies and gentlemen, thank you very much for your patience. This is totally brand new. I'm not expecting everyone to get this right away. Please let me know if you have any questions. We'll do some more problems in class, I'm sure of it. Bye-bye.